Welcome to Calculus. Today we will investigate graphs of derivatives of functions, focusing on interpreting the derivatives graph's traits to reveal information about the original functions graph. We'll take a look at two examples where we start with a graph of a derivative for a continuous function f. So here's our first example if we scroll down slightly. So we've got our function of the derivative, and although the derivative is not continuous, we are told that the original graph is. So we want to answer three sets of questions. So the first set says, does the function, so again, not the graph that we're shown the derivatives graph. We're asking now about the function. Does it have any horizontal tangent lines? So really we just need to identify a horizontal tangent line on a function, how that would show up on its derivatives graph. Well, we can think that on a function, it has a horizontal tangent line when its slope equals 0. So it's either at a maximum value, a vertex, or a minimum value, another type of vertex. And the way that that would show up on the derivatives graph is as a y value of 0. Remember, a derivative is a set of points that describes the slopes of the tangent lines of the original function at those x values. So bottom line, if I'm looking for horizontal tangent lines on a function, on the derivative, I'm looking for x-intercepts. Where do the y values of the derivative equals 0? So I need to find x-intercepts, and I see that on my graph here of the derivative, so this is a graph of y equals the derivative of f of x. I have an x-intercept at -2 and at +3. So I'm going to record both those spots. I have a horizontal tangent line on the graph of the original function at x equals -2 and at x equals 3. And that's where it occurs. We should say y. So these are points where we have horizontal tangent lines because the derivative's y value is 0 here. So we do want to justify why we're saying that. The second item that we want to identify is if the original function has any vertical tangent lines. So like we saw here with horizontal tangent lines, where we can just identify, hey, those are x-intercepts on the derivatives graph. We want to kind of say, okay, if I'm looking for vertical tangent lines, what does that show up as here on the derivatives graph? And basically the idea here is we're looking for some instance of a vertical asymptote. Now, notice the question that pops up second. If yes, why, where does it occur? And this one, is the point a cusp of the original function f? So we do need to remember how vertical asymptotes show up on original functions graphs. And we kind of had two instances where we could have a vertical tangent line on a graph. So let's say we're going to kind of sidestep here and say, let's look at the function. So a good example for this one is a function that has an inflection point. So if I have a graph something like this one, and I'll go ahead and pick a green color for the function, where it changes concavity one direction to the other. At that point, what I've got essentially is what I'm asking here is a vertical tangent line. Now, the way that that would show up on the derivative would be a vertical asymptote. In this case, if I think about the slopes on either side of the function vertical, or the function inflection point, they are positive, they approach vertical, and then they stay positive. So the derivative would look something like a rational function where both sides on either side of that vertical asymptote approached the same direction. We could have that instance for a different type of graph. We could also have both going down. Now, that's the case that is not a cusp. This original function here doesn't have a cusp. It's got an inflection point. So the other possibility could be something like that. And again, the way that would show up on the derivative, in this instance, both headed down to negative infinity, because those tangent lines have negative slope on either side of the vertical tangent line. So these are not cusps. The way we would see a cusp on the derivatives graph is a vertical asymptote that has, in fact, we'll start here with the original type function. So the way a cusp looks on an original function is not with an inflection point where I'm switching over, but one where I'm changing from negative slopes and then quickly changing to positive slopes. So we could have instance where it's up like that, or also considering that it could be in that direction. And the way that that would show up on the graph of the derivative would be as a vertical asymptote where I have one branch of the rational function going down, the other positive. So this is what we're looking for in terms of a cusp. So as I look at this derivatives graph, I see that my vertical asymptote, so returning to the one that we've got here on this example, my vertical asymptote is really like this example. So I do have a vertical tangent line at x equals 0, just to identify that that's that vertical asymptote on the y-axis. It occurs at x equals 0, but it is not a cusp. Not a cusp. And the rationale for that, again, is because both sides of the derivative approach positive infinity from the left and from the right, it would not show this behavior where we have a change in the sign on the slope. Both slopes are positive. Last question here is, does the graph of f have any corners? If yes, why and where does it occur? So we need to remember the difference between a cusp and a corner. A cusp is something that has slopes that approach infinity, so they become vertical. Whereas a corner has simply finite slopes. The thing that makes it different from just a kind of a continuous graph that we could differentiate is that the finite slopes are not equal. So we'll write that there. That's what we're looking for in the derivatives graph. Finite slopes, but not equal. So the place that I would identify that as is these two open circles here on the derivatives graph. Notice these are values. They're open circles, so it means that in some way they're undefined right there. But we have here at x equals 1 a corner. Again, because the slope is finite, it's not approaching infinity or negative infinity. but the two slopes are not the same. So on the derivatives graph, kind of what we're looking for is discontinuous, really a jump discontinuity. Let me include the word jump there because that's kind of a telltale sign that we've got a corner on the original functions graph. We're looking for a jump discontinuity on the derivatives graph. And that pretty much answers this question. So the question says, does it have any corners? It does at x equals 1. And the reason, or where it occurs is x equals 1. The reason why is we are seeing derivative has finite but unequal slopes at x equals 1. Let's take a look at a second example. So again, similar question where we've got the graph of the derivative and we just want to use it to make some inferences about the graph of the function itself. So here's a second derivative graph. Let's give the 100% view there. So again, this is f prime of x. And we're looking for the same item. So again, let's start off with this situation. We're looking for a horizontal tangent line. So just to remind, what we're looking for on the graph is of the derivative is an x-intercept. So on the graph of the derivative, I'm looking for an x-intercept. The reasoning again is that the horizontal tangent line has a slope of 0. And the derivative function is the set of all points that describes the slopes of the tangent lines of the original function at those x values. So that's at the value of x equals 4. So at x equals 4, f of x has a horizontal tangent line. We need to say y. And good justification there is because the y value of the derivative equals 0 at x equals 4. That's the only horizontal tangent line, again, because on the graph of the derivative, that's the only x-intercept. The second question is, does f have any vertical tangent lines? If yes, why? Where does it occur? And is the point a cusp of f? So remember, what we're looking for with vertical tangent lines are vertical asymptotes. So on the graph of the derivative, we're on the lookout for vertical asymptotes. So it looks like we have one here. And that's, if I trace it here, right on the y-axis. So we'll say at x equals 0, the original function has a vertical tangent line. So what I note on this derivative is that on the left, the slopes of the tangent lines approach negative infinity. On the right of that vertical asymptote, the slopes of the tangent lines approach positive infinity. So they're opposite. One's going towards negative infinity on the left, positive infinity on the right. That is a situation where we do have a cusp. And just to kind of make a case, let's pull our examples from above. So what we're looking at, if we compare our graphs to our little key here, we're looking at this instance where I've got on my derivative graph a vertical asymptote with one side on the left, in this case, approaching negative infinity, on the right approaching positive infinity. And what that would represent on the original function is this cusp, where on the left, the slopes are negative, and then the slope becomes infinite. And then on the right side, the slopes become positive. That is a classic instance of a cusp. So we'll record it here. We found it. It's at x equals 0, vertical tangent line. And our reasoning here, well, we should say that it is a cusp. It has a vertical tangent line, which is a cusp, or which represents a cusp on the original function. Represents a cusp on the original function. And we again need to justify, why are we saying that that's the case? Because the limit of the slopes of tangent lines from the left approach negative infinity, while from the right they approach positive infinity. So again, it's that opposite nature where we've got one side of this derivative function headed towards negative infinity, on the other side headed towards positive infinity. So we'll finish that. While from the right they approach positive infinity. Last consideration here again is, does the graph of the original function have any corners? So just like we've done with the horizontal tangent lines and the vertical tangent lines, let's remember what we're looking for on the derivatives graph that would represent a corner on the function. We are looking for finite but unequal slopes. And in terms of the derivative graph, where slope is y values, so finite but unequal y values. And kind of our rule of thumb here is we're looking for jump discontinuities. So looking at the graph, it looks like I've got such a discontinuity here at x equals 1. Notice these are finite, but the y values are different. That's a jump discontinuity. Finite, but unequal y values. So to answer the question, yes, we have a corner on the original graph. The reason is, or let's say where it occurs at x equals 1, f of x has a corner because the y values at x equals 1 for the derivative graph are finite but not equal. So again, just kind of repeating that same idea as a justification for saying the original graph has a corner. Finite but unequal. It's a jump discontinuity. And that completes our second example. So just wanted to definitely show an example where we had a vertical tangent line that was not representative of a cusp. That was our first one. Just to show that again, where both sides are headed towards positive infinity or negative infinity. And then an example where we do have vertical tangent line that does represent a cusp. So thank you for joining for this investigation of graphs of functions and their derivatives and what we can infer from one given the other. Thank you for joining. I'll let you go interpret your derivative graphs. See you soon.